discussed this vector atom model. I'll just revise in brief, very brief. So this is what a vector atom model. This model was thought because of these two effects, Zeeman effect and Stark effect, because earlier models, Sommerfeld model, Bohr model, etc., these models were not successful in explaining this Zeeman effect as well as Stark effect. Then scientists at that time thought that there should be some more other model which will inculcate or which will be helpful or which will be useful in discussing each and every aspect of this spectroscopy. And in that sense, these two basic concepts, as we have seen, are introduced later on in this model, which is called as vector atom model. So first concept is concept of space quantization. So this space quantization is basically an electron orbits or orientation of electron orbits in an hydrogen atom. The electron in the orbit, which is revolving around the nucleus, this cannot select any arbitrary orbits when it is kept in certain magnetic field, and according to that their orbits have certain restricted orientations only. And this is first concept, that is what we have seen to be concept of space quantization. Remember, the space quantization is one of the very important concepts which will be required almost in all further topics or chapters. There are several derivations where this concept of space quantization comes in. So we have to very sincerely and we have to very nicely understand what this space quantization is. And second important concept, as I said, that is said to be electron spin. So even after this space quantization, we found that sodium D lines, that is another puzzle at the time of at that particular time in the spectroscopy. And to resolve that puzzle, people thought that electron may have certain spin. Of course, the spin what we discussed yesterday is not a classical spin, but the intrinsic spin that is provided by nature to this electron, and this spin is responsible for giving some nuclear magnetic moment, spin nuclear magnetic moment. And this is why there has to be certain spin, and this spin is taken to be two values, plus half and spin is plus half, the electron spin is plus half, and its projection over z-axis or the external magnetic field axis direction, this is given by plus 1/2 and minus 1/2. So this is how we have drawn this diagram. Actually here I should have written this to be S is equal to, actually this is 1/2, okay, and its projection is minus half, plus half, and this projection is minus half. So that correction would be needed there. So that is how the spin magnetic moment arises because of the spin angular momentum, and for that there has to be a spin angular momentum or spin quantum number, that is 1/2. Its projection over this H or the external magnetic field is given by ms. So ms is equal to either plus half or minus half, and this orientation, that is also space quantization in case of spin. So these things we have discussed yesterday. Today we are going to discuss the important, as what all these types of parameters we have discussed. These are called as quantum numbers. So what are the different quantum numbers used in this vector atom model? Once we understand these quantum numbers, then it is very easy, as I said earlier, to write the configuration, electronic configuration, or we can write address of any of the electron very easily once we understand these type of quantum numbers. And we have to go for discussion as well, from where this quantum number comes. So from Bohr model, for Sommerfeld model, from this vector atom model, everywhere we have come across these quantum numbers. But there is one more source of quantum numbers, and that is what we have to solve this Schrodinger equation in quantum mechanics. Solve Schrodinger equation for hydrogen atom, assuming this is a proton electron system or positive charge nucleus and electron which are separated by some distance, and this type of proton electron bound system, if it is considered, we go for its wave functions and all these things, that is in quantum mechanics. But in solving all that cases, these Schrodinger equations, we have to apply this method which is called as the method of separation of variables. So r theta phi, these three different types of equations are resolved, and solutions of these equations are again obtained by the series solution method. And in that discussion we come across different constants, and these constants are nothing but these quantum numbers. So quantum numbers, what we define in case of this Bohr, Sommerfeld model, etc., and the quantum numbers which we are coming across in quantum mechanics using this Schrodinger equation, these are just same. So we have just mentioned latest symbols we are changing, otherwise interpretation and meaning of all is just same. So these three quantum numbers, n, spin quantum, that is principal quantum number, L, that is orbital quantum number, and third one is the magnetic quantum number. So origin of these three quantum numbers, as I said earlier too, in mathematical methods of physics also we have looked something about this, that this origin of these three quantum numbers is in the solutions of these equations what we go for, R equation, theta equation and phi equations. And one more this quantum number, as we have discussed earlier, that is spin quantum number. So these four quantum numbers are now sufficient to locate any of the electron inside an atom. एखाद्या ॲटम मधल्या कुठल्याही इलेक्ट्रॉनचं एक्झॅक्ट लोकेशन सांगायचं असेल तर these four quantum numbers are sufficient, and thereby once we understand this method of writing quantum numbers of any of the electron in an atom, then it is very easy to describe or to predict the spectrum of an atom, or if what will happen to an atom if it is placed in this magnetic field, this type of electric field. So this type of changes or effect of that electric and magnetic field also can be calculated, and certain predictions can be done. So that is how this spectroscopy, branch of spectroscopy, becomes more and more popular, as well as accurate and good one, interesting one, when we understand all these type of four different types of quantum numbers. Okay, so give a next title today, quantum numbers associated with, quantum numbers associated with vector atom model. Quantum numbers associated with the vector atom model. So we discuss these quantum numbers associated with this vector atom model. Okay, so in very brief background we'll write here. By solving Schrodinger's equation, for hydrogen atom following quantum numbers following quantum numbers are found, with restrictions, with certain restrictions. Okay, what are these? First one is called as principal quantum number. This is given by symbol n, and restriction upon is this: it has to take values 1, 2, 3, 4 and so on. This is called as quantum values. No fractional values for this n is allowed, and therefore energy of the first orbit, second orbit, third orbit, etc. when we measure, then we have to go for E1, E2, E3, etc. These are the energies, and these energies are found to be in the quantum states, and that is the first basic quantum number that we have to describe. Second, once n is defined, then we come across second, that is called as orbital quantum number, and this is given by L is equal to, it varies from 0, 1, 2, 3 up to n minus 1, and this is again an orbital quantum number. And third one, as we have discussed earlier, that is magnetic quantum number. And symbol used for that is ml. We have seen that this ml varies from minus L, 0 up to plus L. This is what the variation of this. Okay, and as I said earlier, in addition to this, fourth quantum number, that is spin quantum number. Spin quantum number is necessary in vector atom model. Necessary in vector atom model. Okay, so this set of 4 quantum numbers, are sufficient. This set of 4 quantum number is sufficient to describe the location of electron in an atom. This is sufficient to describe the location of electron in an atom. Now let's discuss all these quantum numbers one by one in detail, their importance, their parameters, their other things, their aspects, their relations with each other, and etc. That will go here. So let's go for first. Today we are going to discuss all these quantum numbers one by one. So first one is, as we have discussed now, principal quantum number. Principal quantum number, as it is defined by n, small letter, that is n. Okay, what it does, it specifies the okay, this quantum number, it specifies the orbit number, also size of the orbit, size and energy of the orbit, or the electron in that orbit, energy of electron in an orbit. So this is what description can be obtained from this principal quantum number. So it directly represents what is the orbit number. Based upon that, we can go for its size, smaller, bigger, etc., or elliptical, circular, etc. Actually, that will come to the next quantum numbers. And at the same time, it gives you energy. So we can get expression for this radius and energy as earlier. We have, this is directly from Bohr model. This Schrodinger equation also gives the same values. We have Rn, radius of nth orbit, is given by epsilon 0 h square into n square. This is what n is, the number of orbit, and divide by pi m e raised to 2. So this expression is the expression for the radius of the nth orbit, or the whatever orbit, its radius is given by this. And at the same time, we also have obtained this expression, energy of the electron in that orbit, or the energy of n of particle, it is basically an electron in the nth orbit, is given by minus, in the bracket, m into e raised to 4th divide by, this is 8 epsilon 0 square into again h square into n square. So this is the second relationship we have obtained in the Bohr relationship. Same expression is obtained by the Schrodinger's equation 2, and that's what this particular equation suggests to you. Rn is directly proportional to n square, and this En is inversely proportional to 1 upon n. So this type of relationship, 1 upon n square. So these relationships can be understood. So energy of an electron in the nth orbit is inversely proportional to n square. Of course, it is negative energy, so binding energy goes on decreasing as this electron goes in higher orbit, because dependence on of this energy, binding energy, and the number of the particular nuclei, particular radii, particular orbit, this n, they have inverse relation. So as n goes on increasing very fast, En becomes smaller and smaller, and finally it becomes 0. So for n sufficiently large value, 8, 10, 20, etc., the binding energy almost becomes 0. and that is what the concept we have learned in this Bohr model. Same concept is provided by this Schrodinger's equation 2 when it is solved for this type of hydrogen atom and so on. So this is what we have discussed, and here thus as we are repeating this thing here, the values of n are, the values of small n are, okay, this is called as principal quantum number, and which are given by 1, 2, 3, 4 etc. up to infinity. Don't include n is equal to 0 there. So principal quantum number 0 is not at all allowed. Okay. Now I am just revising these things. All these things we have discussed earlier, doesn't matter, but we are repeating all these things just to understand the basics of this vector atom model. Okay. So and one more thing we have to replace here. Now depending upon that, there is a nomenclature also we use in spectroscopy. So that is called as levels, energy levels or cells. Energy levels or cells. Cells. Now for n is equal to 1, this is called as capital L cell. For n is equal to 2, this is called as K cell, capital K. L, K, okay, sorry, we have written opposite. Not this, should not be this way. Actually, we start from the K. Just a minute. Okay, I'll discuss this. Why it is not erasing this? Okay, I'll write this to be first. N equal to 1 is called as K cell. N equal to 2 is L cell. N is equal to 3 is M cell. K, L, M, N, O, etc. So these are the symbols used for the state n is equal to. N is equal to 1 is K state cell or K energy level K. This is L energy level or L cell, M cell, N cell, O cell respectively. This is what the nomenclature used. Okay, respectively. This is said to be, so n value decides what type of cell is. N is equal to 1, then it is K cell. N is equal to 2, then it is L cell. Likewise, we can go for further. Okay, so now this is started working. It's not, not it. Okay, now let's come to this. So K cell, L cell, M cell, etc. These are the cells which are this nomenclature depends upon what is its n value. And also one more thing, we have studied this, the total number of electrons. The total number of electrons. Total number of electrons in a given cell. In a given cell is R 2n square. So for n is equal to 1, this 2n square gives me 2 electrons. So this is the occupancy or capacity. So 2 is the capacity of this n equal to 1 cell or K cell. So this is K cell for which n is equal to 1 and therefore 2n square gives me 2. Then for L cell, how many electrons I will have there, because n equal to 2. This formula 2n square. This gives me 2 into 2 raised to 4. That is how it gives me 8 electrons. So this is the occupancy or the capacity of the L cell. Then I go for this M cell. M cell has n is equal to 3. So this number 2n square is equal to 2 into 9. That gives me 18 number of electrons. This is 8. Here it is 18 electrons. So this is the capacity of this L cell, M cell, and so on. So or N cell, etc. We can go further, and that's what this particular calculation also shows you, that depending upon in which cell we are dealing with or which cell we are dealing with, the number or the occupancy or the total number of electrons that can be accommodated by that cell is that particular cell can be given by this formula twice n square. Okay, so this is what their description related to this principal quantum number, the number shells, the symbols used, the occupancy, etc., etc. These are the things we will be requiring next when we go for actual different types of 1 electron system, 2 electron system, and so on. Now second quantum number, remember this question is very frequently asked in examination. Describe the quantum numbers in the vector atom model. So this entire description is here there. So second we are going to discuss is orbital quantum number. This is orbital quantum number, and symbol for that is small l. Okay, remember this is number, this is not orbital angular momentum. When I call angular momentum, orbital angular momentum, then it is a physical quantity, it has certain dimensions. But here orbital quantum number is a number, it doesn't have any dimensions. Try to understand this concept again. So this is what so this quantum number arises due to orbital motion of an electron. Orbital, that means just Earth like around moves around the sun. So electron moves around or revolves around the nucleus, and that motion is called as orbital motion. This quantum number arises due to orbital motion of electron around nucleus. That is the origin of this quantum number. This gives rise to the orbital angular momentum. Some books called orbital angular moment, some called orbital angular momentum. Just it is same, orbital angular momentum or orbital angular momentum of an electron. Okay, on the basis of classical mechanics, this orbital angular momentum capital L is given by r bar cross p bar, moment of momentum. Okay, this is what moment of momentum. So classically it is given by L bar is equal to r bar cross p, or further I can write this relationship. L is equal to this, P can be written as m into v, so mass of the particle of the electron into r bar cross v bar. That gives me the orbital angular momentum of an electron moving around this, where m is mass of electron, v is its linear speed of the velocity, and r bar is radius vector. Remember, this is all a repetition of the things, but it is very necessary and important. That's why we are taking this. Okay, so by classical mechanics, L is given by r bar cross p bar, or it is given by L is equal to m times r bar cross v bar, because several times you have to use these relations too in further derivations. But quantum mechanically, now how to write orbital angular momentum in quantum mechanics, the different concept is there, but quantum mechanically actually before that we should write this. Okay, quantum mechanically, the orbital angular momentum L bar is given by L bar is equal to root of L into L plus 1 into h upon twice pi. Remember, as I said on that day too, still you have not learned quantum mechanics. In the next semester you are going to learn quantum mechanics, but how to define angular momentum classically and how to define angular momentum quantum mechanically, these are two different concepts. So representation of angular momentum, orbital angular momentum, classically is shown by this equation above, and orbital angular momentum is quantum mechanically defined by this: L bar is equal to root of L into L plus 1. So remember, this L here is the orbital angular quantum number. So quantum number is L, small l, and based upon that this L bar is given here. Okay, so where this L is orbital angular quantum number. Okay, so again try to understand, this capital L it's a physical quantity, it has dimensions, it has units, but this L, small l, is purely a number. It is an orbital angular momentum quantum number, so that's what it is, a purely number, that is to be understood. And here restriction, this L is given by quantum number, given by, as already we have discussed, this L can have values 0, 1, 2, 3, 4, etc. up to n minus 1. So what is n? Based upon that, L will be decided and n will have its values. Okay, and one more thing here, already we have discussed in Bohr model. Okay, we have second postulate is directly associated with this, that is angular momentum. That is, we have given the L bar of an electron in an orbit should be equal to n into h upon twice pi. This is what our second postulate of Bohr theory. This postulate is directly related to this L bar which we have defined here. So this is a quantum principle. So this quantum principle is one of the very important principle, and this principle, because of this principle only, Bohr could modify the Rutherford model, and further he could give correct explanation of the electron spectrum. So try to understand, this is what the connection between this vector atom model and the quantum mechanics. So Bohr model itself is a semi-classical. It is using some classical concepts as well as it is using some quantum concept, and this is what the concept from this orbital angular momentum has been used by Bohr in his second postulate, and based upon that he could give successful explanation of all the spectrums and so on. Okay, now what is the relationship from this capital L and small l? Okay, so we'll write further the values of L is equal to 0, 1, 2, 3, 4, etc. up to n minus 1, which you have written earlier, n minus 1, etc. represent subcells. Earlier we have used cells, so K cell, capital K cell, L cell, M cell, etc. Now these divided in subcells. These cells are divided by subcells, and this division is given by this small l. Okay, so we can write in short as here, and this is going to be small s, p, d, f, g, and so on. This is symbol used here. So we'll go for this clear cut classification. How we go for this? So for principal quantum number n equal to 1, this is called as capital K shell, and as I know, value for L is equal to simply 0 there, because K equal to 1. So n equal to 1, L will have n minus 1 value, that is only one value, and that L is equal to 0, and that's why this is the S subcell. This is called as S subcell. Then we go for another orbit, n equal to 2. Now this is called as capital L cell. And here L has two values. First value is 0 and second value is 1. Okay, so n equal to 2, we have two values, L equal to 0 and L equal to 1. So it varies from 0 to n minus 1. N is 2, so 2 minus 1 is 1. That's why second value is this. and that's what it is called as S subcell. So this is again S subcell. As long as this small l for an subcell is 0, then this is called as S subcell, and for l equal to 1, this is called as P subcell. This is called as P subcell. And third one, when we go here, now when we go for this n equal to 3, third orbit, now this is called as M cell. Okay, and here also I can have three combinations: l equal to 0, then l is equal to 1, and l is equal to 2, and hence this is called as S subcell. Then this is L subcell, and this is M subcell, small m. So the concept of cell and subcell, that is to be understood. So cell are directly from the quantum numbers, principal quantum number, and subcells are taken from this value of orbital angular quantum number L. So depending upon L equal to 0, 1, 2, 3, etc., these are called as S subcell, P subcell, D subcell, and like that. So sorry, this is not M, this is D subcell. I correct you this. This is called as D subcell. So in SYBC, you might have used this electronic configuration for any of the atom: 1s2, 2s2, 2p6, 3s2, 3d10, and so on. Okay, 4s2, 4p6, then 4d10, and so on. Okay, all these things you might have discussed. So this is first orbit, first subcell, one subcell. Second orbit, there are two subcells. Third orbit, there are three subcells. Okay, and these are this. So n equal to 1, only one subcell. S is equal to, and occupancy of that is simply 2. Total number of electrons there will be 2. In case of n equal to 2, now this is capital L cell. Subcells here are L equal to 0 and L equal to 1, which are called as S subcell and P subcell. And we have seen this can have occupancy 2, and L cell can have occupancy to be equal to 6, and therefore total of this is going to be 8. And that is how there are 8 electrons possible in this second orbit, or L cell, or S subcell of capital L cell and P subcell of capital L cell. So that's how cell and subcell, these concepts can be understood here. Here also this occupancy is 2. Now this is L equal to 1, so there can be 6, and then this D, again this gives me 10 number of electrons can be occupied by this D subcell. So these subcells are the another important concepts in the cell, and the values of the subcell or the occupancy of the subcell, that is decided by this value of small l, or that is your orbital angular quantum number. So this is again we are going to use very frequently in entire our future discussions. So maybe 1 electron system, 2 electron system, or whatever different types of system, doesn't matter. We are going to have this type of nomenclature that will be used in our atomic and molecular spectra. So this is our second quantum number in detail. We have learned that. Now third, this is orbital sir, I am in lecture. मी आता lecture मध्ये येतो. So orbital magnetic quantum number. Magnetic quantum number. Okay, look. Very frequently students get confused between this second and third. Second is only orbital quantum number. Orbital quantum number. Second is only orbital quantum number, and third is orbital magnetic quantum number. That means whenever I am having certain magnetic field, and if that particular atom or that particular electron is kept in this magnetic field, now its orbital angular momentum, that is what space quantization already we have discussed. This concept comes here, and that's why another quantum number comes. That's why it is called as orbital motion is there, and magnetic field is also there. Because of this magnetic field and this orbital motion, the quantum number gets changed, and that is what is created, and the new quantum number That is what we are going to be calling it to be the orbital magnetic quantum number. Okay, so we'll write in brief: if an atom, this is given by small ml, if an atom is placed in weak magnetic field, you can write strong too, or in magnetic field only, doesn't matter. Weak magnetic field H bar, then this is very important concept here, that's what we are writing. Then L bar, orbital angular momentum of electron in that atom, L bar of an electron interacts, orbital angular momentum of an electron interacts with applied magnetic field, interacts with this applied magnetic field. So this interacts with the applied magnetic field. Okay, and that is what we have seen, the principle of quantization. So according to space quantization, or the concept of space quantization, the possible orientations are given by, we have seen this earlier relation, Lz is equal to ml into h upon 2 pi. This is L, this is not L, ml into h upon twice pi, and we have already seen this ml varies. ml goes from minus L into minus L plus 1 minus L plus 2 up to go on increasing, then becomes 0, and then L plus 1, L minus 1, and so on. Which I can still not this, but I'll rewrite this. Let's rewrite this. This is ml is equal to minus L, then second is minus L plus 1, then minus L plus 2, so on, go on increasing this. It becomes, at some stage it becomes 0, and then start increasing, then L minus 2, L minus 1, L minus 0, that is L. So we get the values of ml is equal to twice L plus 1 values, twice L plus 1 values of ml are there. Okay, so if I go on measuring, if L equal to 3, I'll get minus 3, minus 2, minus 1, 0, then 1, 2, and 3. So total values are 1, 2, 3, 4, 5, 6, 7, and that's what gives me 2 into 3 plus 1 is equal to 7. This is called as multiplicity, and that's how we get twice L plus 1 states for this ml. Okay, and now as per our yesterday's diagram, we are going to show one such very important diagram, which we are going to use very frequently in all further derivations as well. Okay, for that I have to get these two shapes. I require these two shapes. Let me take this particular shape here and draw this diagram. Now this diagram is one of the very important diagram we have to use in for further derivations. So that diagram I am keeping it here. So this is an draw some big diagram like this. Actually I could not use this. I should not use this. let me cut this. I'm using this again. So this okay, that's correct. And now take one more shape here, and this time I have to give this shape as what I will do, I'll draw first this cone here. Draw this cone first. So let's draw this cone. I'll take again this line here to draw this cone. Why it is not coming? Sometimes this board becomes a problem. Actually, I needed to draw this type of straight lines. This is a cone. Now it is coming. Okay, that's good. I take this line, and now this is a line here. So if I draw this line from this to this, let's see how it looks. Just a minute. Why it is not drawing? Shape. Okay, let's draw this. Still not drawing. Okay, this board is stuck sometime. Sorry.